Going on now to topic 3.4, other common functions. And in the upper right corner here, I should have a circle with an eye in it that gives you some background as a little review of what will be taught here. Here are the objectives, and we'll get started shortly. Again, you want to take some good notes, pausing as needed. We're going to look at other functions. We've seen linear functions, which look like this, where x is to the first power. We've seen quadratic, where we get the basic parabola. Now, what is the shape of a graph in which your exponent is higher than 2? That is x to the third power, which is an odd power. Well, it has this general shape. How about x to the fifth power? Now, notice what's happening in the area of the origin here. It's being stretched as we increase the exponent in its odd case. Now, how about if it's an even exponent? Well, if it's x to the second, we get our general parabola shape. If it's x to the fourth, notice what's happening. Again, the base near the zero, the origin, is spreading out. And that occurs in even powers. Spreads out a little bit more when it's to the 6. So what we're looking for here is a pattern of the general shapes and then what happens to them. Now, going on to example 1, I'm going to do something I haven't done so far, and that is use the video that the authors produce. They do a really good job and perhaps better skills than I. So what is the example? Power functions of the form ax to the n power, and we have examples A and B, and you'll want to include these in your notes.
In this example, we're going to graph some polynomial functions. Sketch the graphs of the following functions. Part A, f of x equals x to the fourth over 5. This function will have the same basic shape as x to the fourth, but it will be compressed vertically because of the 1/5 factor. So to graph this, we evaluate at a couple extra points. So first, let's evaluate at x equals -1. So f of -1 is -1 to the fourth over 5, which is 1/5. So this gives us the point on the graph, -1, 1/5. Next, we evaluate at x equals 2. So f of 2 is 2 to the fourth over 5, which is 16/5, which in decimal form is 3.2. So this gives us the point 2, 3.2. So to graph this function, we start by plotting the point -1, 1/5. Before we graph this, I'm going to label my axes. So on the x-axis, I have 1, 2, and 3. And in the negative direction, -1, -2, -3. The positive direction of the y-axis, I'll label 1, 2, 3. And in the negative direction, label -1, -2, -3. So to graph, I'm going to plot the point -1, 1/5, which is approximately 1/5 above the x-axis. And I'm going to plot the point 2, 3.2. Since this has the same basic shape as x to the 4th, we know that it also goes through the origin. And I sketch the basic shape of x to the 4th going through the points -1, 1/5, the origin, and 2, 3.2. Part B, g of x equals -x cubed. This graph will have the same basic shape as x cubed, but it will be reflected over the x-axis because of the negative sign in front. So to graph this, we first find a couple extra points. Evaluating at x equals -1, we have g of -1 equals negative times -1 cubed, which is a positive 1. So we know the point -1, 1 will be on this graph. The second point we evaluate at x equals 1. So we have g of 1 equals negative times 1 cubed, which is -1. So the point 1, -1 will also be on this graph. I start by labeling my axes. So in the positive x direction, I need to label 1, and in the negative x direction, I need to label -1. In the positive y direction, label +1. In the negative y direction, we need to label -1. So I plot my points, -1, 1, and 1, -1. And because this has the same basic shape as x cubed and has only been reflected, I know it still passes through the origin. So now I sketch my graph with the basic shape of x cubed going through the point -1, 1, the origin, and then 1, -1.
She did a good job on that. And in the text of Learn, here's what it looks like. Pretty much going over what she said. The nice part about the text is the graphs are, formally prepared as opposed to sketching, but you can see them very well. Even powers higher than 2, the base is just expanded. And then in this one, and I noticed she expanded the graph so she could plot the points well, where if it was x to the 3rd, it would be the reflected image of this, just going the other way. So bringing out the negative aspect of something. And again, using Desmos or your own TI-84s or any graphing calculator shows what it would look like. Looking at other power functions in the form of ax to the -n power, here we're looking at x to the negative 1, remember, would become just 1 over x, where now the variable ends up in the denominator, and then x to the negative 3, x to the negative 5. Notice what's happening to the graphs. Again, you want to sketch this and then feature this, where the curve is getting very close to the y and x axes. If it's to the first power, negative 1, and then if it gets to the odd third power, it gets a little further away. They are expanding, and then to the fifth power, a little further away still. And the key here, these would be odd exponents. Now, moving on, if they are even exponents, pause for a moment and reflect what's going on here. Well, first of all, they're above the x-axis. Similar things are happening that at the x to the negative 2, which is 1 over x to the second, you have this amount of spread at the bottom. If it goes x to the negative 4, there is greater spread, and so on. Notice they are mentioning what is called the range of these, that it never reaches 0. You can indicate that by the parenthesis at 0 over here. Now, what does that imply? They're not mentioning it, but in a sense, your y-axis here is a vertical asymptote that we've mentioned earlier. All right, let's go on. In example 2, they're asking us to graph and sketch this function. Now, notice it's a negative value. X is in the denominator, so it indicates generally this type of graph. But what we would need to do is plug in some extra points. Now, I'm not going to go through all the calculation to get these points, but as we look at them here, we can see they were plotted very, very carefully. Again, showing a vertical and horizontal asymptotes as these fractions get smaller and smaller and smaller. So take a moment to sketch these. And again, there is the example, and putting this into your calculator would look something like this. Now, in this next part, to give you some general background, power functions of the form AX, but now the variable is in exponential form as a fraction. So you may recall that these can be converted. This is its exponential fractional form, can be converted to radical form. So these are equivalent. And what does it look like? Well, again, comparing it to a linear equation, if it's the square root, it's going to look like this, and its reflection on this side as your powers of odd, it looks like so, greater powers like 3, 5, 7 being the index number, looks like this. And I should stress these are odd roots. When your index number is odd, they're extending on both sides. Now, if they're even, and again, pause here, you want to get some sketching. Like square root looks like this. Fourth root, notice the initial part is extended up, but it's that general shape. Sixth root, again, just a little bit more, but the general shapes. This is what you want to sketch. Having good notes that you can rely on and study, very useful. Now, I might ask the question, why is it with odd roots you get this little tail on this end, while with even roots you don't? And the answer would be, with even roots, you can't have a value under the radical sign that's negative. So odd roots, you can have negative values. That's why this line extends here. Even roots, you cannot. Now we're going to take a look at what is referred to as absolute value functions. Remember, the absolute value of something is always 0 or greater. Generally, we say it's positive. So in graphing this, this would be the general shape of an absolute value of something. Now, if there's a negative sign outside the absolute value sign, then it's going to take this graph and just reflect it to the bottom, where it'll start here and then go down. We'll see this worked out here shortly. And here's an example of it that we'll look at in more detail. All right, now I'm going to use the author's video for this as well, something new.
Hi, in this example, we sketched the graph of an absolute value function. Sketch the graph of the function f of x equals -2 times the absolute value of x. Because of the negative, this function is the graph, the absolute value of x, reflected over the x-axis. And because it is multiplied by 2, it has been stretched vertically. So we find a couple points on this graph. So we have that f of -2 equals -4, and f of 2 equals -4. We also have that at 0, the y value is 0. So we have a point at the origin, and we have a point at -2, -4, and a point at 2, -4. So this graph will have the shape of an absolute value function that has been reflected over the x-axis and has been stretched vertically by 2.
And again, there's the graph. And I'd like to review this item of stretching and shrinking. So they're saying it's stretching, it's going further away. Now, how about if it were a -3? For a -3 would look like so, that I've put here in red, showing it stretched more. Now, if it was a 1, the blue lines would go in closer to the y-axis. That would shrink vertically. Now, she had used the words over x. I might have described this as under x, but it's relating to the x-axis what happens in these absolute value graphs. And with technology would look like this. Now in this next part, the greatest integer function, I'm going to ask you to pause it and read it. And I'll give you time and raise it up. Notice that the symbol for this looks like a double vertical line absolute value sort of notation. So we'll raise it up a little. You can finish reading it. And can see what the graph looks like. Again, you're pausing, reading it over carefully. Looking at the graph. Okay, we're going on to our next slide. Now this is our last topic. It's piecewise define function. And I always wondered, where did the name come from? Well, I think of it as a piece of something that we're going to plot, and then another piece of something that we're going to plot, and there are restrictions. So pause for a moment, look it over. There's the definition. You'll be asked to do these in the practice and certify. So we're going to take a look at the author's video to give you the background. And in the practice that I also do, I've picked out some examples. I will go over it, working it out in some detail.
Hi. In this example, we sketched the graph of a piecewise function. Sketch the graph of the function f of x, defined as negative 2x minus 2 if x is less than or equal to negative 1, and as x squared if x is greater than negative 1. Note, always pay close attention to the boundary points of each interval. Remember that only one rule applies at each point. We start on the interval. Negative infinity to negative 1. We include negative 1 because we have that x is less than or equal to negative 1. And on this interval, we have the line y equals negative 2x minus 2. This is the line to graph this line on the interval negative infinity to negative 1. We find a couple points. So when x equals negative 1, we have that y equals 0. And when x equals negative 4, we have that y equals 6. So we plot a point at negative 1, 0, and at negative 4, 6. And we connect these 2 points with a straight line with an endpoint at -1, 0. Next, we look at the interval -1, the parenthesis, to infinity. On this interval, we have the quadratic graph y equals x squared. Note that we still need to figure out what's happening at x equals -1, but now because of the strict inequality, we have an open circle at y equals 1. Another point we have, if x equals 2, then y equals 4. And this graph also goes through the origin, so we have a point at 0, 0 as well. So we graph the point at 0, 0. We graph an open circle at the point -1, 1. And we have a point at 2, 4. And sketch the parabola connecting these points with endpoint, the open circle, at -1, 1.
Now, here in the solution, she goes over it in a much more detailed way, printed out. Again, pause, read as needed. But then in completing the graph, again, such a nice representation here. Questions I could ask, what's the difference between these two blue lines? Well, for instance, this one on the left is linear. That's a straight line, where 0 here is included in the set, where this other line to the right, the curve, is part of a parabola, where this point here, the hollow, is not included. And how would you describe this graph? Well, this is a piecewise. Now, another question I would ask is this a graph of a function? And the answer is yes, it would pass the vertical line test. If we were to move a vertical line over this graph, it would only intersect in one point. You might say here there would be a potential of 2, but this value here is of -1 is not included. Sort of an anchoring point because of the hollow. So this is a graph of a function. Now, what would be the domain of this graph taken all together? Well, interestingly, it's all real numbers from -infinity to +infinity. Now, how about the range of the graph as is shown here? Well, since 0 is included here, we would put a bracket, and that would go to +infinity. Okay, that'll wrap up this lesson, and you'll have your practice. And again, good notes, study, and I thank the authors for their help with the video.